Good morning, everyone. It's almost time now. It's 10 o'clock in Taiwan. And welcome to the online seminar. We call it Crescent, which is, I think, having to do with instrument introduction, emission introduction, organized by TSU, Taiwan Space Union. And I'm Wayne Yip, and I'm the host of this seminar to be given by Assistant Professor Sheral Crescent Tissera. And Sheral, I met Sheral last time, actually almost a year ago at the Bear Garden, after the end of a session at AOGS, and he was sitting next to me, and then we talked until I decided that I must invite him to give a talk here. But it took a long time to arrange, because as you will hear from him, he's very busy. But a few things to first is Sheral, he got his a bachelor degree in engineering in aerospace engineering and a master's engineering degree in electrical and electronics engineering from Nanyang Technical University. And then he got his PhD degree in electrical and computer engineering from National Singapore University. And his expertise is on satellite attitude determination and control. That's also the topic of his talk today. And you will hear from him that he had been working on almost a decade now on a number of very interesting satellite missions, and including the so-called Lumelite series on CubeSat. And of course, his talk is focused on ADCS, which is altitude determination control system. But I think he will describe his lab at NUS for you. So Sheral, please go ahead, please. Thank you so much.
Yes, thank you, Prof, for the introduction. Let me first share my screen. Yeah, hi everyone. Good morning. My name is Sheral. My family name is Tissera. So in this presentation, I'll talk about the development of an attitude determination and control system for an advanced distributed space mission using our very own Lumelite satellite platform. So for those who are not familiar with the term attitude, attitude actually means the orientation of the satellite with respect to an inertial frame of reference. So we need such a such attitude determination and control system to point the camera towards a specific target on ground to capture image, or to orientate the solar panels towards the sun for power harvesting. So it is such a important subsystem in the satellite, and I will talk about some of the development work that we did on this system for our Lumelite satellite programs as well. So I am an assistant professor in the Department of Electrical and Computer Engineering, and as well as the Deputy Director of the Satellite Technology and Research Center in NUS. The presentation outline will be, I will first give a small, very brief introductions to our Star Center in NUS. Then I will talk about the Lumelite 1, Lumelite 2, and Lumelite 3 satellites used in an upcoming distributed space mission. Next, I will dive into the development of an ADCS for this distributed space mission. And then also I will share some of the overall development work that we did for Lumelite 1, 2, 3 satellites. And thereafter, I'll end with a Q&A session. So just to give an introduction to STAR, it is a joint lab between the National University of Singapore and the Defence Science Organization in Singapore. It was set up in the year 2017, and it is located in the Singapore National Wind Tunnel facility here in NUS. The picture on your left, if you can follow my mouse pointer, you can see there are 3 levels in this building, and Star Center occupies 2 levels, the first and the second floor. and occupies a total floor area of about 1,400 square meters. In this facility, we have a class 100K clean room, ESD control laboratories, satellite mission control room, and various other facilities to develop satellites from about 12U CubeSats to all the way to about 125U or 50 to 70 kg class of satellites. So the vision of the STAR Center is to be a world-class center for advanced distributed satellite system using multiple satellites flying in formation, constellation, or swarm. So most of the research work that we do in our research center is aligned with distributed satellite systems. So with that, let me share the name of our satellites. It is named Lumelite, and it is derived from two terms. Firstly is lumen, and secondly is, of course, satellite. Now, lumen is a unit of flux which actually measure the power intensity of a light emitting source. So it resembles a star which is very bright. So we combine lumen and satellite to form a Lumelite or a satellite built-in star. With that, let me introduce some of the satellite programs in STAR at NUS. Firstly, we have our flagship formation flying program, and for this program, we'll be launching 3 satellites, namely Lumelite 1, 2, and 3 to demonstrate formation flying. Next, we have Lumelite 4, which was launched in April last year, and it carries a VHF data exchange system for maritime communication. Next, we have Lumelite 5, Lumelite 6 to 8, which are 50 kg class of satellites to demonstrate satellite data relay system and as well as advanced formation flying technologies. Lastly, we have our student-led Galaxia programs, uh, which is an educational program for the undergraduate students to embark on space development activities. So let me now introduce the flagship program, which is Lumelite 123 for an advanced distributed space mission. This program is named Satellite Formation Flying Program, and it is a project. It's a joint project with the Defense Science Organization here in Singapore, and is funded by the National Space Office in Singapore, which is the Office for Space Technology and Industry. Now, in this program, we'll be launching 3 satellites: Lumelite 1, Lumelite 2, and Lumelite 3. Lumelite 1, which does not have a propulsion system, is referred to as the leader of the formation. Next, we have Lumelite 2 and 3, which actually carries a propulsion system uh, to follow the leader in the formation, and therefore they are known as the followers of the formation. Now, in this mission, Lumelite 2 will be injected after ejecting from the launch vehicle. Lumelite 2 will be injected to a slightly different orbit inclination using the propulsion system. Whereas for Lumelite 3, after the end of the in-orbit testing phase, it will go through a descent on demand mission where the altitude of the satellite or the semi-major axis will be changed from 550 kilometer to about 350 kilometer to enter a very low Earth orbit environment. Now, this program is one of the world's first formation flying program using 312U satellites, and we are building the satellite bus performing the integration, launch, and operation activities using payload provided by DSO. Now, some of the technologies that are on board is that it has the ability to to achieve a precise relative positioning of less than 1 meter. It has a S-band radio link for inter-satellite communication, and also time synchronization less than 50 nanosecond using chip scale atomic clocks. Now the satellites are ready for launch and is planned for the third quarter of this year. Now this slide summarizes the overview of our satellite bus platform. Let me now introduce some of the subsystems. So firstly, we have the electrical power subsystem connected to the solar panels to generate electrical energy from the sun. Now, the electrical power subsystem consists of different submodules. Firstly is the PCDM, which is the power conditioning and distribution module, which is responsible in operating or switching on and switching off all the subsystems in the satellite and providing the necessary ranges of voltages from 3.3 volt to 5 volt to 12 volt to 24 volt and so on. Then we have the AOM, which stands for Array Optimizer Module, which primarily bridges the battery management module and the PCDM with the solar panels. Next, we have the battery management module, which manages an in-house developed lithium-ion battery pack sized together with the solar panels to generate powers of about 100 watt. Next, we have the onboard computer, mainly consisting of the GNSS receiver and the chip scale atomic clock for time synchronization throughout the entire satellite. And its main duty is to actually operate the payloads and also to schedule all the missions that will be carried out on the satellite. Next, we have an important subsystem called the communication system, where it has the radio links to communicate with the ground stations. Firstly, we have a UHF radio link, which is our backup telemetry and telecommand interface with the ground stations. And then we have the S-band radio link, which is the main telemetry and telecommand or TTNC link with the ground station, and X-band for payload data download. Next, we have our structure and thermal control system, where it houses in-house developed deployment mechanisms and also both passive and active thermal control technologies. Next, we have our attitude determination and control system. It is one of the most complex systems on board the satellite and is responsible to reorientate the satellite to conduct the planned payload missions, and as well as orientate the solar panels towards the sun for power harvesting. So what is different in our system is that it is scalable and configurable all the way from 12U to 27U or even up to 125U. So all these blocks that are seen in yellow color is in-house developed within our research center. So we have the ability to do these configurations and scaling up to 125U in a very flexible and within a short period of time. So because of this modularity and scalability, The technology received a patent from Singapore and as well as from the international application. uh, and this technology that we have developed was used in all the Lumelite satellite platforms developed in our research center. Now with that, let me go through the ADCS development and verification that was carried out for our Lumelite satellites. Firstly, I'll start with the requirement. Now, because it is a formation flying mission, we need a propulsion system where two out of the three satellites will carry a propulsion system. The requirement is usually specified in terms of the delta velocity, and the requirement is 100 meter per second. So generally a satellite will fly about 7 kilometer per second. So with this propulsion system on board, we are able to change the velocity by plus minus 100 meter per second. And this number was derived so that we have sufficient delta V for orbit inclination change of Lumelite 2 and descent on demand mission of Lumelite 3, as well as orbit maintenance of the formation of the three satellites. The Because the satellites do not have an imaging payload, the requirement for a pointing control is not very stringent. Uh, it is specified to be less than 3 degree with a slew rate of 2 degree per second. Orbit positioning is something that is critical. So we are using GPS real-time orbit positioning with an accuracy of less than 10 meter when the GNSS receivers are in the visible range with the GPS satellites. Now, when the GNSS receiver is unable to see the GPS satellites, we will be using onboard SGP4 orbit propagator, which can generate the position velocity information of the satellite using TLE up to an accuracy of 10 kilometers. The two tables in the slide summarizes the sensor specifications as well as the actuator specification. So firstly, we have three sun sensors, or we call it the fine sun sensors, with an accuracy of 0.3 degree at 3 sigma. Three sun sensors were selected such that we have the required field of view to conduct the planned payload missions. Next, we have two gyroscope, one high accuracy gyroscope, which actually had a lot of flight heritage on board. Then we have um, uh, a high accuracy gyroscope, which did not have much flight heritage at the time of development. So our IMU-A with a lower accuracy was configured to be the default IMU of the satellite, while IMU-B, which had a higher accuracy, was configured to be the backup or on-demand gyroscope to conduct the payload operations. Next, we have the final sensor, which is a magnetometer, which provides the Earth magnetic field in the satellite body reference frame. For the actuators, we have reaction wheels to produce the required slew rate of 2 degree per second, and magnetic toggles to dump the saturated momentum of the reaction wheel. Now let me share with you some of the development and verification work that we did for our Lumelite attitude determination and control system. Firstly, we start with the verification of the time knowledge that we have in our ADCS system. This is the most important input that is given or that is needed by ADCS for all the algorithms on board the ADCS. So we start our verification process with the verification of the time accuracy on board the satellite. The time is either received from the GNSS receiver or it is propagated on board using the chip scale atomic clock. For the GNSS receiver verification, what we have in our research center is a Spirent GNSS simulator that is capable of simulating the GPS satellites that can be received by the satellite for a given and simulated orbit in the simulator. So with this, we can program the satellite orbit and the start time information in the GNSS simulator, and then uh, we can feed these signals into the GNSS receiver on board the satellite to obtain the position, velocity, and time information. From there, we can calculate the uh, the absolute uh, accuracy of the time on board the satellite. Once the time has been verified, we then move on to the verification of the position and velocity information of the satellite, which is also crucial uh, and is an input to all the algorithms on board, or most of the algorithms on board the satellite. Now, as mentioned earlier, we obtain the position and velocity information either from the GNSS receiver or we propagate on board using a SGP4 propagator using the two line element or TLE information of our known orbit. With that being done, we then move on to the verification of two reference model to obtain the magnetic field vector with respect to an inertial frame of reference in the satellite, and as well as the sun vector with respect to an inertial frame of the uh, satellite. Now, for the magnetic field, we use the International Geomagnetic Reference Field model and as well as a sun model for the sun vector respectively. Once the verification of these models has been carried out, we can proceed with the verification of our attitude estimation. Now, how this works is that the IGRF and the sun model will provide a vector pair in the reference frame, in the inertial reference frame. Then we have onboard sun sensors and magnetometers to provide another vector pair with respect to the satellite body frame of reference. So using these two vector pairs, we are able to calculate the attitude or the orientation of the satellite with respect to the inertial frame of reference. We either use Quaternion estimation or Quest algorithm to calculate a deterministic attitude of the satellite, or we can use the onboard gyros to calculate the attitude with a higher precision using sequential estimation methods such as an extended Kalman filter. with the attitude estimation being verified, we can then move on and verify our control algorithms. So for our satellite, we are using model-based model predictive control scheme for attitude control. And this verification is done experimentally using the sun pointing experiment, where we have uh, hardware in the loop test setup to conduct the sun pointing experiment experimentally in the laboratory, where the solar panels will be facing the sun for power harvesting. Now, with both the attitude estimation and the control attitude control verified, we can now do the verification of the 3-axis pointing using simulations. So these pointing modes includes nadir pointing or target pointing of the satellite to conduct the planned payload missions. Thereafter, we move on to the verification of detumbling algorithms. This is to make sure that when the satellite ejects from the launch vehicle, it can reduce its momentum to a certain level such that the reaction wheels are able to absorb the residual momentum and then perform a 3-axis pointing or even sun pointing to commence the launch and early operation phase of the satellite. So detumbling simply means that you are reducing the body rate of the satellite. When the satellite is ejected from the launch vehicle, uh, there will be a initial or an induced rotation of the satellite by the launch vehicle or by the deployment mechanism to eject the satellites from the launch vehicle. Now, whenever the reaction wheel absorbs the residual momentum from the initial ejection, or whenever there are disturbances on board the satellite, the reaction wheel will absorb this residual momentum, and as a result, the speed of the reaction wheel will increase or reduce to absorb this momentum. As the reaction wheel has a certain maximum and a minimum operating RPM, we need to constantly dump this saturated momentum to a nominal value, so that there is always allowance to impart momentum to the satellite for a 3-axis control of the satellite. Finally, when all the algorithms have been verified, we move on to the flight software acceptance testing, where we will be doing the verification of the complete flight software of the ADCS integrated with all other subsystems of the satellite. With that, we complete the verification of the Lumelite ADCS. Now I'll share some of the results of this verification. We have the SGP4 position vector verification. On the left, you have the position, and on the right, you have the velocity vector verification. So we verify uh, our MATLAB algorithms against a commercial software called Free Flyer. And as you can see from the results, we have a orbit positioning error of less than 0.5 kilometer. However, when we do the verification of the flight software with MATLAB or Free Flyer, you can see that the error increases due to the floating point error calculations in the flight software, which is absent in MATLAB. So therefore, the error can actually rise up to about 10 kilometer, but it is still within the requirement of ADCS. Next, we also do the IGRF and Sun model verification, both against the free flyer commercial software and our MATLAB simulation models. Now, for the experimental setup, for attitude control, we have developed a hardware-in-the-loop spacecraft simulator consisting of an air-bearing spacecraft simulator, a 2-axis rate table for the calibration of gyroscope, a sun simulator to produce a parallel beam to simulate the sun at an output of about 1400 watt per square meter, and it is installed on a stage where we have the ability to change the direction of this parallel beam coming out of the sun simulator. So the most important equipment is actually the air-bearing spacecraft simulator, which actually simulates the near microgravity environment in space, so we can verify our attitude control algorithms in the laboratory. So let me now show you the spacecraft simulator. There are multiple components of it. We have our flight electronics, and this flight electronics is identical to the ADCS flight electronics of the satellites. Then we have the sensors such as the fine sun sensors, the actuators such as reaction wheel, which is mounted on this platform with respect to the uh, flight electronics in the same way as it is mounted in the satellite, so that once the algorithms on board the simulator has been verified, it gives us assurance that the satellite will also functions in the simulated method as in the simulator. We have lithium ion batteries to power up the entire simulator, and it allows us to operate the simulator for about 1 hour, continuous operation for about 1 hour. Then we have wireless CAN receiver, transceiver to communicate, uh, to provide a communication channel between the flight electronics and the mission control software of the Lumelite, so that we can operate this simulator remotely. So in order to simulate this microgravity environment, firstly, we need to uh, do a balancing where the center of mass of this entire simulator is aligned with the center of rotation of this simulator. So once it is properly balanced, you can see that a $2 note, which is very light, can actually move this entire platform. Now this video shows how the reaction wheel operates. So when the reaction wheel operates in a clockwise manner, you can see that the simulator will operate anti-clockwise. So the angular momentum of the platform is conserved. So this also shows that the attitude control of the satellite is based on the principle of conservation of angular momentum. So with this simulator in place, we can perform sunpoint experiment using the solar simulator. So when the simulator is turned on, the platform will move such that the sun sensors of the platform is constantly aligned with the parallel beam produced by the sun simulator. So once the sun sensor is aligned, it will stop rotating and maintain its attitude for solar power harvesting. These are some of the experimental results for detumbling, momentum damping, and sun pointing verification using the hardware in the loop simulator. So we have three portions. The red shows the detumbling phase where the body rate shown in red color is constantly reduced using the magnetic toggles until the the reaction wheels are able to absorb the residual momentum of the simulator or the satellite. So once it is within an acceptable uh, residual momentum requirement, the satellite will start the sun acquisition phase shown in green color, where the reaction wheel will decelerate to 9,000 rpm to absorb this residual momentum. Thereafter, the momentum damping phase will kick in, where the body rate of the satellite shown in red color is will be maintained at 0 degree per second, while the reaction wheel momentum gradually reduces back to 0 rpm. So this experiment was done using our IMU-A, which has a lower accuracy, and the same experiment was recarried out using a higher accuracy gyroscope. So you can see that the noise level of this graph is actually lower than the previous graph. Also, for the momentum damping algorithm, we are able to change the set nominal RPM value. So for example, at 1800 second, we actually change the nominal RPM of the reaction wheel from 0 RPM to 500 RPM. And the momentum damping algorithm is able to follow this change in set RPM. Next, for the verification of three-axis pointing, we have developed a full suite of algorithms in MATLAB, where the satellite is being replaced by a Runge-Kutta integrator to simulate the dynamics and the kinematics of the satellite. So once the reaction wheel produces a torque, the integrator will simulate the resulting resulting quaternion or the attitude of the satellite, and as well as the body rate of the satellite. So once we know these two values, with the time information, we can calculate the position and the velocity using a SGP4 orbit propagator, which then go through the sun model and the IGRF to provide the sun vector in the inertial reference frame and magnetic field vector in the initial reference frame. Thereafter, we can simulate the magnetometer and the sun sensor to simulate the sun vector in the body frame and as well as the magnetometer in the body frame. So we have two vector pairs of sun sensor sun vector and magnetic field vector, which can go through the extended common filter estimator to provide an estimate of the attitude, which is then used by the MPC attitude controller to produce the torque using the reaction wheels, and then the process is repeated thereafter. So we use this scheme to verify three-axis pointing of the satellite, which includes nadir pointing and target pointing. Finally, we have the flight software acceptance testing, where we do general verification of UTC timekeeping and distribution throughout the satellite, housekeeping and whole orbit data download, and also scheduling of uh, necessary missions on board the satellite that is of importance to ADCS. Apart from that, the flight software will also cover GPS PVT acquisition using the GPS signals. Will verify all different pointing modes, and also we will verify the arrival of signal status such that when the satellite is close to the ground station, the ADCS will command the communication subsystem to start sending out the beacon using the S-band radio link. Apart from that, we also do the thruster communication verification to make sure that we can provide or we can command the propulsion system to uh, uh, maintain the formation of the satellite. Finally, we also have a scheme to upload the flight software of ADCS, and the flight software acceptance testing will also cover the verification of this software upgrade capability. These are some of the flight results that we got from Lumelite 4. After calibration, we are able to achieve a pointing error of about 2 degrees using our IMU-A, which has a lower precision. So with IMU-B for Lumelite 123, we can achieve a pointing performance of about 1 degree once it is calibrated during the launch and early operation phase of the satellite. Finally, I'll quickly go through some of the development work that we did for Lumelite 123 satellites. So we do various testing during the EQM stage. We have thermal cycle, the thermal vacuum cycling, vibration and shock, and also end-to-end testing for our engineering and qualification model stage. But when it comes to flight model stage, the shock testing is removed and is being replaced with the flight software acceptance testing. These are some of the pictures of the flight model during various kinds of acceptance testing. So we have thermal cycling, where we do cycling for uh, two, two cycles, where we are changing the temperature from about -20 to about 50 degrees. And then we firstly do the thermal vacuum bake-out, which is required by the launch service provider over a period of 24 hours before we do the thermal vacuum cycling, also for over two cycles. Next, we have the vibration testing to meet the stiffness requirement of 45 Hertz in the lateral direction and 90 Hertz in the longitudinal direction to meet the launch service provider requirement. So for engineering qualification model, we also do the shock testing using the same shaker. Thereafter, we do our CG tuning, and this is because we have a propulsion system and we need to make sure that the center of mass of the satellite is aligned with the thrust vector direction. If you can follow my mouse pointer, this vertical direction of the nozzle shows the direction of the thrust. So we will be doing CG tuning using this instrumentation system developed by us to make sure that the center of mass is aligned with the thrust direction to avoid unnecessary disturbance torque on the ADCS. So the final part of the development is our end-to-end testing, where we will do a complete end to end of our radio link, uh, where the satellite is stationed in the clean room facility, and the signal, all the signals will be sent from our mission control software uh, via an intermediary antenna on our rooftop directly to the ground S-band ground station located in another building of NUS. So with this, we can do the complete end-to-end testing uh, of the satellite prior to the launch. These are some of the pictures of the Lumelite 1, 2, 3 satellite flight model hardware that is ready for launch in the third quarter of this year. These are some of the publications relevant for the development of attitude determination and control system. If you want to find out more info, and with that, come to the Q&A session, and I'm happy to take any questions you guys have.
Okay, thank you, Professor Tessera, for such an amazing talk. So now it's about time for the QA session. So does anyone have any question to the Professor Tessera? Please feel free to turn on your microphone and ask Professor Tessera. Any question? Okay, so here I have one question.
Yes.
Uh, I remember a few years ago, most of the CubeSat were 1 to 3U in size.
Yeah.
But by 2023 to this year, the trend has shifted to 12U to 27U. And I even saw one in your presentation was 125U, right?
Yeah.
So what are the benefits for this larger CubeSat? And is that a trend toward large CubeSat going to continue in the future?
So the one of the requirement, one of the main reason why larger CubeSat starting from 12U to 125U is attractive is because it can accommodate larger solar panels and larger capacity for the onboard lithium ion batteries, so that you can either operate high power payloads, or you can operate low power payloads for a longer duration of time. So basically, throughout the orbit, including the eclipse period where there is no solar power energy available. So 12U and 16U satellites can still be deployed using a standard commercial off-the-shelf deployer. So, and these 12U and 16U are actually the biggest CubeSats that are available. So therefore, it is very attractive. But if the size is still not enough, then you are looking at 27U or 125U, where we will not be using a CubeSat deployer, but more of a ring-based adapter for the separation system.
Okay, okay. It's a very nice to see more CubeSat in the space. Yeah.
Yeah.
So any question?
Hi,
Hi.
can I ask some question?
Yes, sure. Go ahead.
Hi, Professor Tissera. I want to ask about the CG adjustment when you
Yes.
integrate the propulsion system into the satellite.
Yeah.
Because there are very seldom paper related to this issue. So can you tell me more about this? Thank you.
Yes. So you can see that the thruster nozzle is coming out of the satellite, and we have actually positioned this nozzle at the center of the satellite. So, or it is aligned with the geometric center of the satellite. So the center of mass, or the CG of the satellite, is actually the center of rotation of the satellite. So whenever the satellite moves, the satellite actually moves, whenever the satellite rotates, the satellite actually rotates about the center of mass of the satellite. Okay, so these are the dynamics of the satellite in space. Now, if there is an offset between the thrust vector and the center of mass, then we will actually have a resulting torque while the thrust force is being applied. Now, this will produce a disturbance torque on the ADCS, and as a result, the reaction wheels will absorb this this momentum produced by the thrust force due to the offset between the thrust force and the center of mass. So we want to try to minimize this residual torque produced by the thrust force as much as possible. So what we do is we do a CG tuning such that the center of mass of the satellite is aligned with the thrust vector of the propulsion system. So of course we cannot make it perfect. So we came up with the requirement that the center of mass should be within 5 centimeter offset from the thrust vector. And our simulation results have shown that the disturbance torque produced by this 5 centimeter offset is well within the operation by the reaction wheel, so that the momentum damping algorithm can comfortably reduce this momentum being absorbed due to the offset of 5 centimeter.
Okay. Thank you, Professor Tissera. Thank you for your good answer.
Thank you.
Thank you.
So any other question? Here I saw a question from 太空自探, right? So the question is the propulsion SQ real time on the orbit or just command by the ground station? How does it integrate with ADCS?
So the propulsion system for this program is actually centralized control. So centralized control means that we are uploading the maneuvers by the propulsion system through the ground. So it is currently not automated, where the propulsion system is manually controlled from the ground station. Now the operation of the propulsion system is actually done through the ADCS. When we are going to fire the propulsion system, we need to align the thrust vector or the plus x-axis of the satellite. So this thrust vector, right, is actually the x-axis of the satellite. So we need to align the thrust vector with the velocity vector of the orbit. So ADCS will either align the thrust vector in the positive direction of the velocity or opposite direction of the velocity, depending on the maneuver requirement, before we actually fire the thruster. So this is how the ADCS is involved in the operation of the propulsion system. And apart from that, like I mentioned earlier, there will be disturbance torque produced by this propulsion system due to the offset between the center of mass and the thrust vector. So another duty of ADCS is to absorb this momentum produced by this due to this offset, and to make sure that the satellite is very stable during the propulsion maneuver. I hope I answered the question.
So is that okay for 太空自探? Is Professor Tissera's answer is okay? I think it's good. So,
Hello.
okay.
Professor Tissera, thank you for the detailed answer. We have a follow-up question regarding the previous one with the synchronization of the ADCS and the thrusters. So
Yeah.
this another question is about, we would like to ask, how does the satellites synchronize during the formation flying? Do you integrate the ground station, or does the satellites use their inter-satellite communication?
No. So the inter-satellite communication is mainly used for payload related activity and as well as the time synchronization. Because with the ISL link, we can actually do some ranging, and we have the chip scale atomic clocks on board, so we can synchronize the time of the 3 satellites in the formation. So that's and also for payload related missions, we'll be using the ISL. Now for the formation maintenance, how we do is we have the position, velocity, and time information of all the 3 satellites, either from the GPS, GNSS receiver on board the satellite, or we have TLE information provided by, for example, NORAD in USA. So on ground, we can constantly monitor the formation, and we can control the propulsion system on both Lumelite 2 and Lumelite 3 such that the relative intract separation between the satellites are about 50 to 80 kilometers apart. So we do a monitoring of the formation from ground and manually control the propulsion system to keep it within the formation.
Thank you for the question, Professor.
For the answer.
For the answer, sorry.
No problem.
Sorry. Is there any other question for Professor Tissera? So if there are no more questions, I think it's about time. So let's once again thank Professor Tissera for today's talk. And we will have 2 more online seminars on June 21 and June 25. So please visit the TSU website for more information. So thank you all for joining today's talk, and we will see you next time. Thank you, Professor Tissera, and thank you all the audience. Thank you.
Thank you. Bye.
Thank you. Bye-bye. Thank you.